So welcome to part two of this test number one review practice exam. We did 1 through 15 on part one. We're going to do 16 through 27 on this video. And we're going to start off with question 16. It's from section 1.5 on quadratic models, and it's the projectile motion application problem. So what we do, we have a football that's been kicked in the air. It's going, because of gravity, it's going to be following a projectile motion quadratic model parabola that opens down because of gravity. Here is our model. We need to find the x and y coordinate because we want to find how far the ball travels along the ground. So we have to find the vertex, and the vertex has an x and y coordinate. So here I go. My x coordinate is negative b over 2a. Remember, my a and b come from the model. So I have my b value is 1.42. I plugged it in there. Here comes the negative from my equation, my minus sign. 2, and my a is negative 0.033. So I have negative 1.2 over negative 0.066. My x coordinate is 21.5. Since we're dealing with a football field, my units are going to be 21.5 yards. So I'll put that into that formula, put it into the flight of the football's graph. I have the x coordinate. My y coordinate, remember, all I have to do is take my model, and wherever I have an x, plug in the 21.5 yards. So I plugged in the x coordinate, which is 21.5, into the model wherever I had an x. I have negative 0.33, and I have to square 21.5. That's going to give me 462.25. I'm going to multiply those two together and add. So I multiply these two, and I get negative 15.3. I add that to 30.5. I would get a y coordinate of 15.2 yards. There's my x coordinate. There's my y coordinate. Let me write that up here. And I'm done with the problem. All I have to do is answer what I'm solving for. How far does the ball travel along the ground? This y coordinate is your maximum height. 21.5 is the distance from where the ball is kicked to the vertex along the ground. To get the total distance, I would have to add another 21.5 together. So when I add these two together to get how far the ball travels along the ground, I would get 43. My answer is choice A. So that was a lot of problem and a lot of steps to do there, but there is how you would do that from start to finish. The x and y coordinate formula, and then doubling the distance along the ground, get the final answer. Number 17, a lot shorter. We have a model. If we were to graph this model, what would this model yield? X is squared. That tells me it's a quadratic. That tells me I would have a parabola. This a value, negative 2, is negative, obviously, so that would be a parabola that opens down. My answer is choice C. X is squared, a was negative. I'm done. Let's take a look at number 18. Here we get into exponential models. And here we have x is an exponent. That tells me I'm either going to have exponential growth or exponential decay. And that's dictated and determined by my b value, the base. My base value here is 1/4, and that's 0.25. 1 divided by 4 is 0.25. And now that I have my base is less than 1 or 0.25, I know I'm going to have exponential decay. If my base would have been something greater than 1, I would have had exponential growth. That's exponential decay because of the b being less than 1. Let's take a look at number 19. Number 19, I've highlighted this. We've been given a model. This is exponential growth. This is out of section 1.6. I want to make a prediction of the population of the United States using this model in the year 2020, and this model was created in 1970. So what I have to do is figure out what value I'm going to use for t to evaluate this model for. And I'm going to choose 50. And the reason I'm using t is equal to 50 is because there are 50 years between 2020 and 1970, so my t is going to be 50. So let me plug in 50 wherever I have t. My e is 2.718. My t is 50. So I plugged in 50 into the model. So the population after 50 years, I'm going to do a lot of calculator work here. 2.718. 0.018 times 50 is 0.9. So the population after 50 years is 200 times 2.718 raised to the 0.9 power is 2.459. I multiply those two together, and where that 2.459 came from is that being evaluated. That is 4.918 in my calculator. I would have about 492 million people. There's how I would do that one from start to finish. This evaluation in your calculator, 2.718, hit your exponent key, your x to the y key, or your caret key, depending on what calculator you have. That will yield that value. So there is that problem. The next one, number 20, is very similar to that. We want to make a prediction of the value of a stock given this model. The company began its existence in 1996, and we wanted to see what the value of the stock was in 2015. So here we go. Again, I have to figure out what I'm going to evaluate this model for t, and I'm going to use 19 for this one. Where did 19 come from? Well, the company, we're looking for its stock in 2015. The company was born in 1996. Company is 19 years old. We're looking to find the value of the company after 19 years. My E again is 2.718. My T is 19. I'm going to add 15 on at the end. A lot of calculator work here. 2.718.15 times 19 is 2.85. I'm going to add 15 onto that. This 2.718 raised to the 2.85 power, 17.28 plus 15, I would have the stock value at $32.28, or about $32. Again, that value is found in my calculator using the exponent key, the x to the y key, or the caret key, depending on what type of calculator that you have. Number 21, writing this exponential equation as a logarithmic equivalent. Logarithm. This is out of section 1.7, base 5 of 625 equal to my exponent 4. Going around 5 raised to the 4th power is 625. 22. Going the other way, the logarithm of 10,000 is equal to 4. Don't forget, when there's no value as my base, it's an understood 10. 10 raised to the 4th power is 10,000. Again, my choice is B. Next one, using your calculator with the natural log. Let me just review this real quickly with you. I happen to have a graphing calculator. I'm going to enter in natural log. Natural log of 125 would give me 4.828. My answer is choice D. If you have a cell phone, you'd enter in 125 first and then the natural log key. Number 24, I want to write this expression out as a logarithm. There's my base 3. There's my 1/9. There's my exponent. 3 raised to the -2 is 1/9. The next one, going back to the calculator, my logarithm of 72 is going to be 1.857. Answer for that is choice A. So that was a quick hitting calculator problem. I have 2 more to go. Let's take a look at number 26, determining what type of graph we have for this model. X again is an exponent. E is my base, is 2.718. My base is bigger than 1. With my base being bigger than 1, I'm going to have exponential growth for my shape of my graph. B is bigger than 1. You're always going to have that value. Last one, number 27. It's out of section 1.7 on logarithms. What we want to do here is we want to make a prediction about the final adult height of a 10-year-old female. So what I'm going to do is I'm going to evaluate this model for the 10-year-old girl at x equals to 10. So the final percent of adult height is 29 plus 48.8 log 10 plus 1. I plugged in 10 into the model. So I have 29 plus 48.8 log of 11. Calculators. 29 plus 48.8. This value in my calculator is 1.041. I have the P of 29 plus 48.8 would be 50.8% of adult height that a 10-year-old female has reached, be 79.8% her final adult height. So there is how you would do that one and all of these problems on this practice test. If you know how to do the problems on the practice test, you'll do fantastic on the real test on chapter 1.